Okay, so what we're going to do in this at this point is do a quick example of a momentum type problem. And so what you can see here on the back of your sheet, you'll see that there is a question that I posed about change in momentum problem. So what you're going to do is we're going to read that question on a separate sheet, just follow the solution. You'll probably be able to figure it out on your own, but that's okay, we'll do it together. Consider a car that is traveling at 25 meters per second. It is coasting along the road when it encounters a rough dirt road. The car decelerates at 15 meters per second, and it takes 5 seconds to do this. So we're assuming it's coasting, right? They're not pressing the gas, not pressing the brake. It's just the friction and the dirt road and the forces acting upon it, maybe some air resistance, whatever the case may be, but it's slowing the car down significantly. Well, the question asks, just what is the change in momentum of the car? Like, we could figure out the acceleration easily, v2 minus v1 divided by the time. So 25 minus 15 is 10 divided by 5 is 2 meters per second. So we can find the acceleration quite easily, but it asks for the change momentum of the car. So really we have to look at what was its initial momentum, what is its final momentum, and what is the difference. So in this question we know that v1 is 25 meters per second and that v2 is 15 meters per second, and the time interval is 5 seconds, and the mass of this object is, we're going to assume, I didn't write it in here, we're going to put that the mass is 1,000 kilograms. So add that to your sheet. You can't do this without knowing the mass in this case. So part A, if we want to find the momentum change, or the change in momentum, which remember is the impulse, we just find delta P. Okay, so we know that that's really just P2 minus P1, like so. So what is the final momentum? Well, the final momentum is just mv2 minus mv1, so the change in momentum. Momentum's easy to calculate, so it's 1,000 times 25, 15, minus 1,000 times 25. So our change in momentum, in this case, is the vector, is negative 10,000 kilogram meters per second. So it's reducing its momentum by 10,000 units, or 10,000 kilogram meters per second. Part B asks, what is the impulse? Well, impulse is by definition literally the change in momentum. So therefore, the impulse is negative 10,000 Newton seconds. Could I write kilogram meters per second? Absolutely. But I'm going to write it as Newton seconds. This is typically how we write impulse. Impulse units. But they're identical. They're exactly the same. Newtons per second, kilogram meters per second, identical. No difference whatsoever. An impulse is nothing more than our simplification of saying, instead of saying change momentum, we just say the impulse acting. So we know that the acceleration would have been negative, which is clear because we get a negative impulse, which means that we would have had a negative acceleration. Part C. Compare the units. Well, Newton seconds from part B is a kilogram meter per second from part A. Well, what is, so what I'll do is I'll multiply the seconds across. That's something that we're definitely able to do. Just multiply the seconds up here. So I get newtons seconds squared equals kilogram meters. Okay. Now if I divide by seconds squared, I get kilogram meters per second squared, which, if you recall from grade 11 and from this year, if Newton's second law is sigma F equals ma, that has units of kilograms meters per second squared, or meters per second. So this is the definition of a Newton. And clearly, 1 Newton equals a kilogram meter per second squared. So that's another link to show you how the units are consistent with one another. Okay, part D. Calculate the average net force during this collision or this interaction of the car with the dirt road. So all we need to figure out is what is the average net force. Well, we go to our equation. It's a vector. Okay. Impulse is the average net force times the time, which equals the change in momentum. They're all the same thing. So what we're going to do is we're just going to look at this part of it right here. So we're just going to look at this part here. So the average net force is simply the change in momentum over the change in time, which we know is really just Newton's second law. M delta V over delta T, or MA. This is Newton's second law. Please remember that. It's the same thing. It's no different. Well, at this point, the average net force acting on this car would therefore be negative 10,000 Newton seconds divided by 5 seconds. So the average net force is therefore negative 2,000 newtons. So knowing this, if we divided this by the mass of the car, which was 1,000, we get the acceleration, which we already know is 2 meters per second negative, right? Because V2 is 15 minus V1, which is 25, is negative 10. Negative 10 divided by 5 is negative 2 meters per second. If the average net force is negative 2,000 newtons, and we divide it by the mass of 1,000, we get negative 2 meters per second. So it's consistent, once again. Okay, in the next tutorial, what we're going to look at is problems where the net force is time variant, meaning that the force acting on the object changes with time, and we're going to see how we can solve problems of that nature. And then we'll be able to work on our assignment from there.